All right. So, hello everyone. In this video, we are going to take a little bit of a small interlude and discuss a special class of solutions to the Maxwell's equations, to the Maxwell's equations without sources. These are the electromagnetic waves, electromagnetic plane waves, is what we're going to discuss. So towards the first part of this lecture video, we are going to discuss electromagnetic plane waves in vacuum, and these are solutions to the Maxwell's equation without sources. So as we have seen before, the Maxwell's equations, the local Maxwell's equations are our starting point of the discussion of this whole thing, and we ultimately want to solve these local Maxwell's equations for arbitrary sources, which are let's say some localized charge density or current density, that we want to do when there is an arbitrary time dependence, etc. So that problem we will solve. But before we go on to that problem, there is a simpler class of very interesting solutions, and these are essentially these EM waves or electromagnetic waves. And so again, electromagnetic waves can be discussed with a lot of detail. But here I'm just going to touch upon the subject a little bit, only highlighting a few things that I will need later on in my discussions. So you will learn more about electromagnetic waves in your optics course, of course. And so also I want to emphasize the fact that here we are going to talk about electromagnetic wave solutions. So here we are going to talk about the electromagnetic wave solutions in vacuum, which means that I'm going to solve the vacuum Maxwell's equations and find these solutions. Of course, electromagnetic waves also exist inside matter, and as we will see later, we can write down some effective Maxwell's equation inside matter, and then we can see that a very similar kind of solutions like the electromagnetic waves in vacuum also exist for the effective Maxwell's equation inside matter. Okay, so this effective equation we are going to discuss sometime later in the course, and this is not what we are going to talk about today. So today we are only going to focus on the source-free Maxwell's equation. These are the source-free Maxwell's equation as I have written down, and these equations has been written down in vacuum. So basically here there's only one combination of mu naught and epsilon naught that appears here, and this happens to be a very, very special combination, as we'll see very soon. So our task at hand is basically to try and solve these set of equations for the electric and magnetic fields, and the point is, the question is whether or not there are any interesting solutions for this system. Basically we'll see that there exists a very interesting class of solutions for this system, and these are essentially the electromagnetic waves. And let's proceed with first trying to algebraically manipulate these equations and cast them into a slightly different form. Okay, so if we take the time derivative of Faraday's law, which is this equation, then we can write down this statement here. Okay, and the time derivative goes through the curl, and we have the curl of time derivative of E, and we have a time derivative squared del t square of B here. Okay, on the left hand, on the right hand side. So now this del t of E, this equation, again by Ampere's law, can be written down as the curl of B. So if I write that down, and of course, I have compensated for this factor of mu naught epsilon naught and taken it on this side of the equation. So if I write it in that form, then I will have the curl of the curl of B, and the curl of B is basically nothing but the Laplacian acting on B. This is because there's an additional term which is basically the gradient of the divergence of B, but because the divergence of B vanishes, therefore that term is not there, and this only reduces directly to the Laplacian acting on B, and this term has a double derivative of time acting on B, again, electric and magnetic fields can depend on time and space. So this is this becomes the effective equation for the magnetic field, or rather, we can manipulate, in this way using one additional time derivative on Faraday's law, and we can land up on equation which has the electric field completely eliminated. Okay, so in case of time dependence, as we can see, the electric and magnetic fields are coupled, these are coupled PDEs. But if we do this manipulation, we see that the electric field gets eliminated, and we can write down one single equation for the magnetic field. Okay, so and as you can identify that this equation is like a wave equation for the three components of the magnetic field in Cartesian coordinates. Okay, so this is like a wave equation for the magnetic field, right? So now also we can do the similar exercise for the electric field. Now we have to take the time derivative of Ampere's law. If we take the time derivative of Ampere's law, then we can take the time derivative inside the curl of B, and then again replace the time derivative of B using using Faraday's law, and write this as curl of E. Okay, once we write this as curl of E, and of course, because we have taken a time derivative on both sides of the equation, this became a double derivative of double time derivative of the electric field on this side, and the mu naught epsilon naught was originally there in Ampere's law equation. So now basically, after using Faraday's law here, this again becomes the curl of the electric field, again because the divergence of the electric field is zero because there are no sources, or there are no charge densities. Therefore, we can conclude that this curl of E is simply nothing but the Laplacian acting on E with a minus sign that takes care of this sign here. And also this other term, which is the double derivative with respect to time, and that also remains. So we see that both the E and the B satisfies a set of wave equations, and wave equations without sources. These satisfy homogeneous wave equations. So if we start from the Maxwell's equation without sources, then we land up with these two equations for the electric and magnetic fields. Firstly, they are separated equations, and they are wave equations for the individual components of the electric and magnetic fields. Okay, so if we work in, let's say, the Cartesian coordinate. So basically we are now, we know how to solve for the wave equation. So, we are going to write down various solutions for the wave equation. So right. So basically we know, so basically, this is the idea. Now we have to take these two wave equations and try to write down solutions of these wave equations. That's it. So these are, if we write down solutions of this wave equation, then what we'll get are these so-called electromagnetic waves. Okay. So particularly in this lecture today, we are going to focus on electromagnetic plane waves, and I'll explain to you, what I mean by plane waves. Okay. Also, as we go along. So basically, we know that these wave equations are solved by sine and cos functions, where this is the combination where k dot x plus minus omega t, this is the combination which is the combination which solves the wave equation. And so basically we can take all these kind of sine and cos for various values of omega and superpose them to get a non-trivial solution for the wave equation. Okay, but for the sake of simplicity of this discussion, we will focus on what is called monochromatic waves, which is a solution to the wave equation for a single frequency. Okay, so this we are going to consider that there is a single frequency. Of course, we can consider similar solutions for many frequencies and superimpose them, and we'll get a very non-trivial solution. But here, for the sake of the discussion, to keep the discussion simple, let us focus on monochromatic plane wave solutions to the source-free Maxwell's equation in vacuum. Okay, so this is the form of the solution. Again, you can think of this as an ansatz, where this E naught and B naught are vectors. So these are two constant vectors, as well as this k vector is also another constant vector. So there are three vectors in the game, which is E naught, B naught, and k vector. This k is sometimes referred to as the wave vector, because it represents the direction along which the wave would be propagating. Okay, so this is like a propagating wave, and k is the direction along which the wave would be propagating. Okay, both, again, this omega can both be plus and minus, and this k can also be so this can be in general any vector pointing in any direction. And the only thing we'll see that as a consequence of the wave equation, this k and omega should be related in a specific way, which we are going to see very soon. And that is what we are going to do. So we are going to take this ansatz and plug it back into the two equations that we had for the electric and magnetic field. Those were two wave equations. Now, once we plug in this form of the solution back into the wave equations, we'll see that both the wave equations imply this particular condition for k and omega. So this k square is basically k dot k. Okay, so this is the magnitude of the k vector. So that k square must be equal to mu naught epsilon naught omega square. Okay, which follows from this equation. So basically, you can see that if I take in this ansatz and plug it back in here, for instance, take the electric field and plug it back in here, then you can see that from this Laplacian, there will be a minus k square, because this is exponential ik. So there will be a ik dot ik coming from here, and that will give me minus k square. And this also is going to give me a corresponding minus omega square. So this is going to give me this condition, therefore. Okay, so similarly with the magnetic field, a similar condition would be obtained. Now, once we have obtained this condition, we will say then it is very simple to see, therefore, that given this form of the solution, this is the so-called monochromatic plane wave solution that solves the wave equations, both the wave equations for the electric and magnetic field, and provided that omega is related to k in this specific way. Okay, so this is called a dispersion relation in vacuum, where this mu naught epsilon naught is identified with the velocity of the electromagnetic wave in vacuum, and this c is basically is this number 1 over root over mu naught epsilon naught. And as you know that this is the velocity of light in vacuum, and its value is 3 into 10 to the power 8 meter per second, roughly around that ballpark. Okay, so basically, I mean, if you know that recently our units have been readjusted so that this value of c is basically a complete integer. It's a very large, it has as you can see, it has a very large number of digits, but it is again rounded off integer. It's not a fractional value. So there has been a recent readjustments of unit which rendered this c to be some very like large integer. So basically this is again our so large integer in SI units, that's what I mean. The meter has been readjusted. Yes. So right. So now we can so these are the solutions, and we can be happy and just so we have found a solution to the wave equations, the two wave equations, but there's a big catch out here, okay, which we have to be aware of. Okay, so let me try to explain that there is a little bit of a caveat in what we just did. Okay, and this caveat is kind of important, and it's going to also be important for our later discussions. So let me explain that caveat to you. So you see, there were these two equations, okay, satisfied by both E and B, and we found that these were the two solutions provided omega is equal to c square k square. These are the two solutions to this. These are the solutions to this equation, to this set of equations, right? Now, it is very easy to see that besides this set of these solutions, we can also have another set of solutions where just this E is this expression and B is 0. And or we can have E is 0 and B is this expression. Okay, so it seems I have missed a B naught vector here. Okay, so B is this expression and E is 0. So if we take both these expressions and plug it back in here, if B is 0, of course this equation is satisfied, and E is of this form, then this equation is satisfied, provided K and omega is related in this way through this relation. Okay, so now so you might think that there is a class of solution which is like this, plus there is a class of solution which is like this, plus there is a class of solution which is like this, and there are three classes of solution to this separated equation. But so turns out that this one and this one are not valid solutions of Maxwell's equation, the original equations which we manipulated to get these two wave equations. These two class of solutions does not satisfy that original Maxwell's equations. Okay, it is very easy to see, because if you see that if you write down the Faraday's law or the Ampere's law, and if B is 0 and E is non-zero, then this clearly is violated. Okay, unless the curl vanishes, which in general it doesn't. So in that case, these will be ruled out solutions because they don't satisfy the original Maxwell's equation. So although they satisfy these two equations derived out of the Maxwell's equation, but they don't satisfy the original Maxwell's equation, and that is a problem because we want to find out solutions of the original Maxwell's equations, right? So in the process of taking derivatives and separating out E and B fields, therefore, we see that we have introduced some redundant solutions, and therefore in any solution that we write down to this set of equations, we have to go back and check whether or not they satisfy the original Maxwell's equations or not. So let's do that. We have claimed that this is the form of the solution, of our solution. Of course, these two solutions are immediately ruled out because they don't satisfy Ampere's law or they don't satisfy Faraday's law in vacuum. So basically, this is the only hope that can work. And so let's take these solutions, and so these are clearly solutions of these two equations. So let's take them and see what is the implication of the original Maxwell's equations for these solutions. Okay, let's check them one by one. So if we do that, then we'll find the following. If we start with the Gauss law, this will say that my k vector, the wave vector, is perpendicular to this E naught vector. This amplitude vector that we have, this E naught vector, this is the amplitude vector. And this one is, the k vector is perpendicular to this E naught. Okay, that's the first conclusion. Similarly, for this divergence of the magnetic field equal to 0 would imply that the k vector or the wave vector here, k, this one is perpendicular to the B naught vector as well. So we see that this wave vector here is perpendicular to both E naught and B naught. That's the conclusion from the first two equations. Okay, and in the second two equations, the Faraday's law and the Ampere's law, we see that k cross E naught is equal to B naught. Okay, and k cross B naught, this vector is equal to E naught. So essentially, this implies that K, E and B, they form basically a system of three orthogonal vectors, and so this implies, as you can see from here, so E is perpendicular to K, so K cross E is something which is perpendicular to both K and E, and that is B. Okay, and B we know is also perpendicular to K. Okay, from here. Okay, so basically these three vectors are essentially perpendicular to each other. And also, it must happen that this omega must be equal to plus minus c times k. Okay, if omega is equal to plus minus c times k, then we can conclude that the magnitude of E naught must be related to that of B naught by a factor of c. Okay, so if you just manipulate this, so you bring the k down, or bring the k down in this equation, then it will be omega by k. Then you will see that omega by k is basically c. So you will see that magnitude of E equal to c times magnitude of B. Okay, this is just a fact. Okay, it just comes out. Okay, so this is how the amplitudes are related. Okay, so basically these three vectors form a set of orthogonal vectors, and they can be oriented in any way in space. Okay, so given k, which is the direction along which the wave is propagating, so this is k, and then we see that E naught is some vector along some direction, and so this E naught, k is, let's say, along this direction. This is the direction of propagation of the wave. This is the wave vector. Then E naught and B naught must be perpendicular to each other and lie on the plane which is perpendicular to k. Okay, and also E naught and B naught must be perpendicular to each other. And if we consider the simplest set of solutions, then we'll see that E naught basically fluctuates yeah, along a given direction, okay, it just moves up and down like this along a given direction perpendicular to k, and the b also in an orthogonal manner, they just oscillate along a given direction at a particular point in space. They perform this kind of this thing. Okay, so here I'm assuming, I'm making some assumptions just to give you the idea, what is going on. So this is the idea that k, e and b, they will form this mutually orthogonal, they form mutually orthogonal directions, and then their magnitudes are related in this way. And of course, omega is related to k in some specific way. Omega equals to plus minus c times k. Okay, so these are the various things, and also it should be noted that we cannot really have an additional phase in the magnetic field. Both the electric field and the magnetic field must be in the same phase. Otherwise, these sine and coses from these two terms wouldn't have cancelled. So both the electric field and the magnetic field must be also in the same phase. If we want, these terms to cancel out in this equation for the Faraday's law and Ampere's law, then it must be that there cannot be any additional phase here. Otherwise, that would be a problem. So basically, yeah, right. So here we are talking about the simplest set of solutions. So right. So basically, the electric field oscillates in a given way here, orthogonal to this k vector, and the magnetic field is perpendicular to it, and it also oscillates perpendicular to both E and K, and both the oscillation of the magnetic field and the electric field happen in phase. And so basically, this is the nature of the solution of the electromagnetic waves. Okay, the plane electromagnetic waves. Now, why are they plane waves? So this is the summary. Okay, these are this is the nature of the solution, and these are the conditions that k has to be perpendicular to E, and k has to be perpendicular to E and B both, and B has to be perpendicular to k as well. Okay, so why are they plane waves? Because as you can see from this expression, that at a given instant of time, there is if I define a plane with the given a wave vector at a given instant of time, if I define a plane with the equation k dot x equal to constant, then this defines a plane, and on this plane the phase of this let's say this electromagnetic wave, this is constant at all points on this plane, because k dot x is constant. So because the phase of the wave is constant at all points on the plane, therefore these are called plane electromagnetic waves. Okay, these are called plane waves. Okay, so and that plane is defined by k dot x equal to constant. This is the plane. Okay, so with this, let me again. This is all I have to say. I wanted to say about the plane wave solution. The main thing is that there exists this kind of solutions which I'm definitely sure all of you have seen before. And one of the important takeaways is this identification of this constant. This mu naught epsilon naught. That is identified with the speed of light. This is one of the important takeaways from this discussion, that the speed of light in vacuum is given by 1 over root over mu naught epsilon naught. These were the constants that were appearing in the Maxwell's equation, and we have been carrying them around for a long time. And now wherever the mu naught epsilon naught combination appears, we can replace it by 1 over c square wherever it appears. Okay, so we will do that from now. Very good. Okay, so again, before going back to the general Maxwell's equations with sources now, let me also finish this discussion of plane electromagnetic waves with a small discussion of polarization. Okay, this idea of polarization, let me introduce here. And again, you will do this in much more detail in your optics courses. But let me just touch upon that and say a few things about polarization, particularly for the monochromatic waves. Again, if I have the opportunity, there are very interesting, this idea of polarization is actually, very deep. And so if I have time towards the end, then I might actually come back to this discussion once more. But again, I think, whatever I'm going to say right now would be enough for us to just proceed with with our objective in this course. So so what is polarization? This idea of polarization essentially is given, let's say, some monochromatic plane wave. So there's a direction of the electric field. Okay, of course there's a, let's say, some wave vector, and there's a plane which is perpendicular to the wave vector. So the electric field must be doing something on this orthogonal plane, right? So this direction of the amplitude of the electric field in the orthogonal plane defines for us, what is the polarization of the electromagnetic wave. What this electric field is doing, that will tell us what is the polarization of the electromagnetic wave. Okay, so now as you can see that if there is one way in which the electromagnetic wave, so let's say there's some plane, and there's some plane like this, and this wave vector k. Okay, and it can happen that the electromagnetic wave is oscillating along some given direction in this plane wave. Okay, then if this is oscillating in a given direction like this, so at a particular point at various instants of time, let's say the amplitude or the electromagnetic field is oscillating along this direction, and therefore the amplitude is pointed along this direction n. Then this is called linearly polarized light, and in the direction n is called the direction of polarization. Okay, so that's the first thing. Okay, to realize that this E, if this is a constant vector and pointing in a single direction in the orthogonal plane, then this is a plane polarized. So this is a linearly polarized light, and also sometimes it is called the plane polarized light, and this linearly polarized light essentially this linearly polarized light is basically there. So there can be, in this way, there can be two directions of linearly polarized light, because there are two linearly independent directions in the orthogonal plane. Given a wave vector, then there is an orthogonal plane, and this orthogonal plane has two independent directions. So the linear polarizations can be of two independent directions. Okay, now that is the idea. Okay, so again, just to elaborate this point once more a little bit. So basically, when I say that my electric field is of this form, what do I actually mean? I always mean, when I write down it in the exponential I, in this language, then what I always mean is whatever I have here, I should take the real part of that, or I can also take the complex part of that, doesn't matter. Just throw the I. Okay, so I can take the imaginary part of that as well. Okay, and work. So I can here I'm supposed to, my convention would be to take the real part of this, whatever appears here, and then that is my electric field. That is my unwritten convention. When I say that my electric field is this, I automatically mean that I should take this and take the real part of it, and then analyze that solution. Okay, the real part of the solution is the real electric field. Okay, this is just, this complex notation, it's just notationally convenient to work with this complex notation. Otherwise, we have to keep on multiplying, causes and sines and etc., which can be very painful. And like multiplying exponentials is super easy. You just add them in the, whatever is there in the exponential, you can just add them. So this is why this complex notation is super easy to use, and people use it. It's very common. But the main idea is that whenever you use this complex notation, you have to remember that the actual electric field is given by the real part of whatever you are writing here. So now, if you have this this E naught vector is a real vector. Okay, if the E naught vector is a real vector, then it is essentially some E1 vector times E naught, where this E naught is a real number, and this E1 vector is pointing in some unit vector perpendicular to k. Okay, so this E1 vector is some possible vector, and then if I take the real part, then this will be E1 vector times E naught, because E naught is real. Okay, I'm assuming that this is the real vector. Okay, and then this is the form of the electric field, and as you can see, this electric field oscillates along the direction of E1, and we will say that this monochromatic wave is basically linearly polarized along the direction of E1. Okay, that's how we will say that this solution is. Okay, now if you consider, this is the point, that if you consider a point in the direction of propagation, let's say x equal to 0, okay, then this actually oscillates in the direction of E1 about that point. Okay, so K is this way. This is what I was saying. Let's say this point is x equal to 0. Then E, oscillates in some direction of E1 vector. Okay. So similarly, it can also oscillate along the direction of the E2 vector where E1 is perpendicular to E2. Okay, so there are two linearly independent possible linearly polarized light and linearly polarized electromagnetic waves. Two independent solutions are possible for this linearly polarized light, and the reason for that is essentially there are two independent unit vectors in a plane which is perpendicular to the k vector. Okay, that's the main reason why there are two linearly independent polarization directions which are possible here. Okay, very good. So that we are these two linearly independent mutually orthogonal vectors are called I'm referring to as E1 and E2. Okay, I'm also assuming that E1 and E2 are mutually orthogonal. So let me actually draw this diagram, otherwise this can be a little. So if I draw this diagram, let's see if I have space. So if I draw this diagram here, tiny diagram, so this, what I mean is there's a linearly independent, there's a plane of this thing, and this is my k, let's say my k direction. Okay, and then there can be any direction which is E1, and then there is a orthogonal direction E2. Okay, so E1 and E2 are unit vectors which are orthogonal to each other. Okay, and they then basically if my electric field is along E2, if my electric field is along E1, then my magnetic field will be along E2 because they are also perpendicular. But here we are focusing only on the electric field. So the electric field can either be along E1, the electric field can either be along E2, or it can be along E2. So these are the two independent orthogonal directions towards which the electric field can point. Okay, because this plane can only be spanned by two linearly independent vectors which we choose to be orthogonal, and these we call to be E1 and E2. If you like, these are the x-axis and the y-axis, and you can choose your axis so that this direction of propagation is the z-axis. Okay, so that's the idea. So this is a linearly polarized monochromatic wave. However, this is now gets a little complicated if this E0 is a complex vector. Okay, it is possible that we were assuming that the E0 is a real vector, but it's also possible that E0 is a complex vector. And if E0 is a complex vector, then we can do the following. Okay, now here I'll go through a little bit of an argument. So if E0 is a complex vector, then E0 dot E0, this is E0 square, this is a complex number. Okay, if this is a complex number, let us assume that the argument of this complex number is -2 alpha. Okay, so if the argument of this complex number is -2 alpha, I can write this E0 square, which is E0 dot E0, as modulus of a complex number, E0 square, modulus times e to the power minus I2 alpha. This I can write. So because this is a complex number, I'm just writing the complex number as some real number times e to the power something. Okay, so this is possible to write, and with this we can say that my E0 originally is of this form, that it is a b vector times e to the power minus I alpha. Okay, this alpha is same as the alpha here. Okay, where the phase of E0 squared is -2 alpha. Okay, and this minus alpha is basically, we can say, is roughly speaking we are extracting it out and writing it outside. So b can also be a complex vector. E0 is a complex vector, b is a complex vector in general. Let's say b1 and b2. Okay, these are complex. So if it is a complex vector, I can write it as a combination of two real vectors. So this one, b1 and b2 are real. Okay, b1 and b2 are real. So this is real. Okay, these are real vectors. So any complex vector I can write in this way. And also I have taken this thing out, so that now if I take the E0 dot E0, okay, that will come out to be b squared, and which needs to be real. Okay, so if b has to be real, then you can just and b is of this form. Okay, so if b dot b has to be real, then it implies that b1 b1 dot b2, these are orthogonal. Okay, otherwise this is not going to be real. Okay, so therefore the general structure, because of this argument, the general structure for this E naught is this b naught b times e to the power minus I alpha, where the I alpha is some phase which goes in here into this exponential. Okay, but this b has this interesting structure. We can always write this b in this form, that it is a sum of two vectors b1 and b2 with a I, where b1 and b2 are mutually orthogonal. Okay, so we can select b1 and b2 if they are mutually orthogonal. It can be written as in terms of these orthogonal unit vectors e1 and e2, and multiplied by some coefficient which tells me what these vectors are, right? So these are the magnitude. b1 and b2 are the magnitude of these real vectors, and e1 and e2 are mutually orthogonal vectors. So b1 and b2 had to be orthogonal by this condition, okay, because b square had to be real. Okay, b square is equal to this e naught square mod of that. Okay, because if I take this and find e naught dot e naught, okay, e naught square, then I see that my phase is e to the power minus 2 alpha, and that will cancel this. So I'll be left over with e naught square mod. That has to be real, and that is exactly given by b square. And this b square is again given by b dot b. And if that has to be real, then b1 dot b2, these two real vectors must be mutually orthogonal. And we choose it to be of this form, where this b1 and b2 are non-zero numbers. Okay, and multiplied by these mutually orthogonal vectors e1 and e2. So this is the most general structure. This form of the E is the most general structure. There can be a phase and there has to be a B, and this B has the form that it is b1 plus ib2 and b1 plus ib2, where b1 and b2 are real vectors which are mutually orthogonal, but they can have different magnitudes, b1 and b2. Okay, so that's the for. If this is the for, then again what we have to do is to take this and find the real part of this. So if you are to find the real part of this, as you can see from here, so this, let me just quickly write it down here so that it's easy to follow. So if b, this is b1 vector plus ib2 vector, okay, and I'm taking the real and imaginary parts of this whole thing. So this is multiplied by this exponential, and I'm taking the real and imaginary parts. So there will be one term which is this b1, this is real. So this b1 e1, b1 is this b1 e1. So this is the real part, and the real part of this exponential, which is the cos, the cos function. Okay, that would be one term, and the other term for the real part would be when this term is basically multiplied with the sign of this, but there are two i's, that is giving you a minus sign, and that minus sign has been incorporated in both the terms. Okay, so cos of minus x is equal to cos x, so it doesn't matter. So in this also I have incorporated a sign, here also I have incorporated a sign. Okay, so if you see, there's a sign off. So in general, the electric field will have this form. This is the most general. We have just argued that this is the most general form of the electric field, which is a solution to the wave equation. Okay, of course, when we write it down in the complex notation, then the magnetic field also will have must satisfy all these constraints that follow from the Maxwell's equation, and it is entirely given by this complex amplitude of the electric field. Okay, this magnetic field is entirely determined in terms of the complex amplitude of the electric field, just because of the fact that it has to satisfy the Maxwell's equations. All right. So now, if you look at this most general form of the electric field, you will notice that. Let's fix a point. Let's say that we are at let's say k is along the z direction. First we can do that just to simplify our life. K is along the z direction, and in that case we can write this as kz, and so in that case we can take e1 to be along the x direction and e2 to be along the y direction. Then ex will be b1 cos of this, and ey will be b2 sine of this argument here. Okay, these arguments will just enter here. Okay, that's what we mean. So now if we consider a single point on the z-axis, which is z equal to 0, let's say, okay, then basically these two expressions reduce to these two these expressions here. And as you can see, with time, if we eliminate time from this relation, then I get this equation, okay, where this equation is the equation of an ellipse if b1 is not equal to b2. Okay, they have to be real numbers by our construction. And if B1 is not equal to B2, then this is a ellipse. This is the equation of an ellipse. So what does that mean? Instead of moving in a single direction, what it means is, this electric field in the orthogonal plane, so let me just draw this orthogonal plane. Right. So in this orthogonal plane, this is the direction of K, let's say. So the electric field actually is rotating, it's rotating like this, and tracing out this, it is tracing out this ellipse as it rotates, and that equation of the ellipse is given by this equation. Okay, this ellipse, this is the equation of the ellipse, which is given by, where the edge of the electric field, the edge of the electric field, if you draw it here like this, that rotates along along the direction of an ellipse if B1 is not equal to B2. Okay, and again remember, this B1 and B2 are these two numbers that are different in the x component and the y component. Again, the x and the y components are essentially the directions orthogonal to the direction of propagation of the wave, which is the z direction. Okay, so this is the idea. And if the electric field rotates in this fashion, so remember, for linearly polarized, there was one particular direction. Okay, let's say there was one particular E1 direction, and there was this electric field was essentially oscillating along this one direction. Okay, for the linearly polarized waves. But for elliptically polarized waves, these are called elliptic. For B1 not equal to B2, and if they are not equal to 0, okay, they are called elliptically polarized light. And these elliptically polarized light, this electric field, instead of oscillating along a single direction, it kind of rotates along the direction of this ellipse with time, because if we eliminate time from these two equations, we get this equation. So with time, it is like rotating in this elliptic fashion. Okay, so this is why it is called elliptically polarized light. And if the magnitudes of B1 and B2 are equal, then you can imagine this ellipse becomes a circle, and then in that case it is called circularly polarized light. Okay, and it is also easy to see for circularly polarized light, if you take the ratio of the two amplitude, complex amplitude along, let's say, x and y, if you write it as a complex amplitude, okay, so the Ex is this, Ey is this, then this is B1 is equal to B2. Okay, so basically you will get, if you consider this to be the complex quantity, okay, if you consider this to be the complex quantity, then basically, there will be a I here. There will be a I here, okay, because B, if you remember, was equal to B1 plus I B2, okay. Again, B1 and B2 can have either signs, plus or minus, doesn't matter. So, there can be a relative sign between B1 and B2. Okay, so if there is a relative sign between B1 and B2 and their magnitude is same, okay, then, so if B1 and B2 are real, even then there can be a relative sign between B1 and B2. If their magnitude is same, it's also always circularly polarized. And depending on the relative sign of B1 and B2, we will get this E0x divided by E0y, this ratio will be always plus minus I. Okay, so these two independent directions, that if you write it down in the complex notation, then their ratio of these two independent directions, that always boils down to plus minus I for circularly polarized light. Okay, so that's the conclusion. So if either B1 is 0 or B2 0, then it is very clear that if B1 is 0 or B2 0, then we'll have oscillation along either E1 or E2, and that will be the case of the so-called linearly polarized light, which we have considered before. Okay, so that is what there is to it. Basically, what is the thing? Most generally, the electric field can actually rotate along the direction, along an elliptic direction, depending on these values of B1 and B2, for a monochromatic light. Firstly, a monochromatic light is always polarized because by definition it's always polarized. Its electric field is doing something. Okay, either it is moving along an ellipse, or it is moving along a circle, or it is going up and down along the same direction. If it is moving along an ellipse, it's called a elliptically polarized light. If it is moving along a circle where magnitude of B1 and B2 are same, then it is called circularly polarized light. And if it is moving up and down along a single direction, then it is called linearly polarized light. That's the simple picture. And of course the magnetic field is also here. So the magnetic field is perpendicular to the electric field. Magnetic field is perpendicular to the electric field, and the electric field, the magnetic field, and the K, they form this right-handed system. And if the electric field rotates, so does the magnetic field, because the magnetic field in B0 is entirely determined in terms of the E0 through the Maxwell's equation. Okay, very good. So that is all I had to say about polarization. I will give you a problem where you can show that if we mix up or superimpose two plane or linearly polarized light with some given phase, then we can get elliptically polarized light or circularly polarized light in general, by this linear superposition. Okay, this I'll give you as an exercise to show. Okay, again, a bit of nomenclature here. So, E1 and E2, we can write down something like, a combination, which is like, so in general, this was E1 plus E2, plus minus IE2. This is circular polarization because you can see both the magnitude of B1 and B2 are same when I've written it in this way. So basically, there are two directions, depending on plus, B1 is plus B2 or B1 is minus B2. In both cases, we have circularly polarized light. So depending on that sign between B1 and B2, we can have two directions. One is E1 plus IE2 and the other is E1 minus IE2. So both these cases will be circularly polarized. I am talking about the direction of the complex vector, which is E0. Okay, so that direction can be E1 plus IE2, or that direction can be E1 minus IE2 in the complex notation. And the one with the plus sign is called left circularly polarized. This is just a terminology. And the one with the minus sign is called the right circularly polarized light. Also, there is a notion of helicity, which I am not getting into any detail of. Again, if you understand this, that these are also two linearly independent vectors. They are two linearly independent complex vectors. Okay, and depending on these two linearly independent complex vectors, we can also have two linearly independent circularly polarized light. One is the left circularly polarized light, one is the right circularly polarized light. Just like plane polarized light can be of two polarization, one is along E1 and the other is along E2, two orthogonal polarizations. And similarly, the circularly polarized light can also be of two kinds. One is the left circularly polarized and the other is the right circularly polarized light. Okay, so depending on the mutual sign of B1 and B2, that is determined whether it's left circularly polarized or right circularly polarized. Okay, so with this I will basically terminate the discussion on polarization and electromagnetic waves. And that is all I have to say about electromagnetic waves. But before finishing this video, I will quickly go on to a little bit of discussion about the most general electrodynamic problem in the presence of sources, and introduce this idea of scalar and vector potentials together for the case of most general electrodynamics. Okay. So let me, continue with this lecture in this video and talk about the scalar and vector potentials in electrodynamics. Okay. So if I let me just switch over, to this vector and scalar potentials in electrodynamics. Okay. So I will just, do this discussion and then stop this video. So, so basically now we have been looking at the homogeneous Maxwell's equation. Or rather the Maxwell's equation without any sources, and we've seen how electromagnetic waves or plane polarized electromagnetic waves are solutions to plane electromagnetic waves which are polarized. These are solutions to this homogeneous wave equation that can be derived out of this Maxwell's equation without sources. Okay, so that's what we have seen in general. And now now we are faced with the most general problem of finding solution to the Maxwell's equation in the presence of arbitrary sources. Let's say we can assume that these sources are localized, and so we again start with these fundamental equations, which are the Maxwell's equations. We want to solve for the electric and magnetic fields in terms of the sources, the charge density and the current density. But now previously we had considered electrostatics and magnetostatics where there were no time dependencies at all. But now we are going to consider the most general time dependent problem and try to solve it. Okay, that's what we are going to do now. And of course, along with these fundamental equations, there's this, again, there's one thing which is again fundamental, which is this Lorentz force. Here I have written the Lorentz force density. You can take this and integrate it to find the Lorentz force. And apart from this, there's a consistency condition that implies that this current density and this charge density satisfies this equation, and this equation is basically interpreted as the local equation for conservation of charge. Okay, the time derivative of the charge density must be equal to minus of the divergence of the current density. Okay, so this is a statement of the conservation of charge. Okay, so this is our starting point, and we are going to solve for this Maxwell's equation. So if you look back at our discussion in electrostatics and magnetostatics, what we did was first try to write down the electric and magnetic fields in terms of certain potentials, and thereby solving some of the equations firstly. And then after we have solved some of the equations, that implied that there were some more equations to be solved for these scalar and vector potentials, which we can look at and then finally solve the problem in general. So we have both for the electrostatic problem and the magnetostatic problem, we have solved for arbitrary localized sources, and we could do that. Okay, in both the cases it was some kind of Poisson equation. Okay, so and once we learned how to solve Poisson equations, then we could solve any problem in electrostatics and magnetostatics. All we have to do is to integrate. Okay, that's it. Okay, so very good. So now we want to do a similar thing for electrodynamics as well, where there is a non-trivial time dependence in the electric fields, in the magnetic fields, as well as in the sources. That means the charge density and the current density can also be time dependent. Okay, so under that situation, what do we do? So basically, firstly, let me emphasize that in our previous discussion of electromagnetic waves, we have seen that this combination of mu naught epsilon naught, which appears here, that can be written as 1 over c squared. Okay, so now even if I'm not talking about electromagnetic wave solutions, I am going to use this constant c wherever it appears and replace this mu naught epsilon naught combination with this c constant c. It's very convenient to do that actually. Okay, and if we do that, because this combination keeps on appearing in all the equations, and if we replace it with c square, then it becomes a very compactly written thing. Okay, it simplifies. Okay, so this is what I'm going to do. So please remember, I'm not talking about electromagnetic wave solutions anymore, but still I have identified this particular constant with the speed of electromagnetic waves in vacuum, and therefore everywhere where this combination appears, I can use this C wherever this combination appears. Okay, that's what I'm going to do. Very good. So now let's see. So first let's start with the equation for the magnetic field, which says divergence of the magnetic field is equal to 0. Okay, this is also true even if there is a non-trivial time dependence in the magnetic field. If this is true, then we can always write the magnetic field as the curl of a vector potential. Okay, this is what we have done in magnetostatics. Only thing is that this time dependencies was not there. Okay, so we could take this we could take this magnetic field and write this as a curl of a vector potential, because the divergence of the magnetic field is 0. This is always possible, and as soon as we write it as a curl of a vector potential, then it is very clear that the divergence is of b equal to 0 is already satisfied, because if we take a divergence on this equation, the divergence of curl, this is going to be equal to 0. Okay, as an identity. So this equation becomes an identity as soon as I say B is equal to curl of some vector potential. So we are going to do that even in the most general time dependent problem. So this A is called the vector potential. Okay. So now if we try to note that contrary to magnetostatics, now we have non-trivial time dependence in both B and A. Okay. Now let's take this definition of B and plug it into Faraday's law. Okay, this is Faraday's law for you. Okay, curl of E equal to minus del B del T. So if I plug it in here, then I have a del T of curl of A, and I can now just manipulate this equation and take the curl on this side of the equation. Okay, once I take the curl on this side of the equation, then I have this combination E minus del T of this vector potential. This thing should be free of any curl. So the curl of this combination must vanish. And as we know, if the curl of a vector vanishes, then that vector must be, it must be possible to write that vector down in terms of the gradient of a scalar field. Okay, so now notice earlier the electric field was just curl free, so you could write down the electric field as a gradient of a scalar field. But now it's this combination of the electric field minus del T of this vector potential that is basically giving me something which is curl free, and therefore it is this whole combination that I can write as the gradient of a scalar field. Again, the minus sign is a convention which is kept there so that it matches with the convention in electrostatics. So in electrostatics, if everything is time dependent, this term just drops out and we have the electrostatic case. Okay, so that is as simple as that. So therefore this is identified with the scalar potential in electrostatics, but now there's a dynamical situation. So we have this additional term in the electric field. So we see that this vector potential not only determines the magnetic field here, it also contributes to the electric field through its time dependence. Okay, that is the new feature that we have here when we put together the electric field and the magnetic field in a non-trivial time dependent scenario. Okay, so as I have just argued that if I write down the electric, just to summarize, if I write the electric and magnetic fields in this form, in terms of the scalar and the vector potential in this way, then we see that the divergence of B and the curl of E equation, both these equations are immediately solved. Okay, because we have used this. As soon as curl of A is equal to 0, if I take a divergence on this is immediately 0. So this equation is solved. Okay, if I take the curl of E on this equation, if I take the curl of E here, then it is very clear that I have to take the curl of this. So basically, I have to take the curl on this side also. Okay, so curl of the gradient that would vanish, and the curl on this term would give me a del T of curl of A, and that is going to give me curl of A is basically B again, so that's del T of B, and here I'll have the curl of E. Okay, so we just need to take a curl of this equation to get this Faraday's law here, and we have to take the divergence of this equation to see that this is divergence of B is equal to 0. So both these equations are solved as identities once we recast the electric and magnetic field in terms of the vector and scalar potentials. Okay, so but there are two equations that are still left, and I would like to highlight the fact that these are the two equations with the sources. Okay, the equations without the sources, they vanished, they become identities, but the equations with the sources still remained, and they are the ones that we have to solve to know what is basically these scalar and vector potentials. Okay, they are the leftover equations, right? And also I would like to note that the scalar and vector potentials, they are like, four functions, because it's 3 components of the vector potential and 1 component of the scalar potential. And because there are 4 functions, here also we have like 4 equations in some sense, that, this Gauss law is 1 equation, it's a scalar equation, and we have this Ampere's law is basically a vector equation, so there are 3 components. Okay, again there are more subtleties about this point, about number of equations and unknowns, but at least the number of equations now matches exactly with the number of functions that we need to solve. But we'll soon see, there's another problem that will come up very soon, and again, there are various layers or various answers to this question of, whether the number of equation is equal to the number of fields that we are solving. Okay, so but at least at this point, it is somewhat nice that we have the 4 these unknown fields, which are the 3 components of the vector potential and 1 component of the scalar potential. Okay, the one scalar potential, and then we have like 3 equations. Okay, Yeah, just the fact that I want to highlight is among the three equations, only one of the equations have time dependence, and sorry, three of the equations have if you like, here there are this equation that has some time dependence, and this equation is more like without any time derivative at all. Okay, well, that's a very curious fact that why is this equation without any time derivative? Okay, but this equation is without any time derivative, whereas this equation has some time derivative at least. Okay, let me just point that out, and we'll, if again if time permits, we'll get back to this discussion again. Okay, so now we have this vector potentials, and we are trying to write this equations down. What are the equations for the scalar and vector potentials? So in Gauss law, if I substitute the form of the electric field, then I can, this is the form of the electric field. I have taken the minus sign out here, and now this will give me the Laplacian on phi, and this will give me a term which is the time derivative of the divergence of A. Okay, so this is the equation that I need to solve in order to know phi and A. Similarly, if I look at Ampere's law, then I can plug in this magnetic field as the curl of a vector field here, and again this curl of vector field can be written as the Laplacian on the vector field minus sign with a gradient on the divergence of A. Okay, this just is equal as a vector identity, and again this term remains, the source term remains, and the electric field here can be written in terms of the scalar and vector potentials in this fashion. So once we write that, we can write this term out. There are these terms here, these two terms follow from here, these two terms here. So there is a double time derivative on A, and there's a gradient of the time derivative of phi. So also there's a gradient of the divergence of A. So we can basically group the terms together. We see that this one and this one fits into a nice combination, just like the wave equation. So let us write them down in the combination as it appears in the wave equation, right? So in the wave equation also a combination like this appeared. So let us write this combination down. And apart from this combination, we have this term and this term here, where we see these are both gradients. Okay, so let us club that these two terms together and write it as gradient of something, and this something is basically the divergence of A plus 1 over c square del phi del t. Okay, this is the combination. Okay, and of course the source remains as the source, and we have written it here. So I think I'm missing I'm missing a minus sign on this source. Okay, I'm missing a minus sign on this source. Okay, very good. So if you just do this manipulation, this comes about. Right. Right. So now we can take these equations and try to solve for the phi and A. But before we try to do that, again, as we have seen in magnetostatics at this stage, we had seen that there was a redundancy in the description in terms of the vector potential. So let's see how that happens. What happens to that redundancy in this case where there is a non-trivial time dependence. Here we see that if we shift this vector field with this gradient of the scalar, and this is what I was calling as gauge transformation for magnetostatics, then we see that the electric and magnetic fields are not really invariant if we just shift the vector, the vector potential. Okay, so along with the vector potential, if we also shift the scalar potential with the time derivative of chi, so now the chi is a scalar field which can depend on space as well as time, right? So if we take, in the time dependent scenario, if we take and shift the vector potential with the gradient of the chi, and if we shift with a minus sign the scalar potential with the time derivative of chi, then we see that both the electric and magnetic fields are invariant. Okay, so this is the statement of the redundancy. Okay, so the redundancy is still there. Now it is a general, this redundancy is characterized by this general one function of space and time. Okay, so one scalar field of space and time, both. Okay, so just to see that, so if I shift the A, let's say, B is curl of A. So if I shift the A by this gradient of chi, then the curl of the gradient, that vanishes. So B remains invariant. Okay, it remains as curl of A here. Okay, so B remains invariant. Similarly, for the electric field, so the electric field expression is basically this, gradient of phi minus del del t of A. Okay, now if we shift it, we shift the gradient by the del chi del t, this term, and a we shift by the gradient of chi. Now if we just put them together, then I have the gradient of phi minus time derivative of a, coming from here. These two equations, these two terms I keep, whereas here I see this is plus gradient of time derivative of chi, and this one is basically, let's see, so, right, did I miss a sign here? I think I messed up a sign here. Oh, this sign should be plus, I'm sorry. Yeah, our gauge transformation is such that A goes as plus, because A goes as with the plus sign, this sign should be plus. If this sign is plus, then this sign is minus, whereas this sign, these two signs give you a plus sign here, and this sign gives you a minus sign here. So therefore these two terms cancel pairwise, and we are left with this, and the electric field therefore remains same as before doing this gauge transformation. So this chi again, if we shift both a and phi in this fashion, that we shift a with the gradient and phi with the time derivative of a scalar field, then we see that both the electric field and the magnetic fields remain invariant. Therefore the physical situation remains invariant, and therefore this chi characterizes a redundancy of description of the physical situation. So this is called a gauge transformation. This chi is called the gauge redundancy, and we need to fix this gauge redundancy somehow, right? Like we did before with a gauge condition. So if you remember, before we fixed a gauge condition which was called the Coulomb gauge condition, okay, which was basically the statement that the divergence of A is equal to 0. Okay, in magnetostatics we chose the Coulomb gauge. Even in the electrodynamic case, we could have chosen the Coulomb gauge and worked with it. It's a completely fine gauge to work in. But we'll see that, there's a particular simplification if we choose a slightly different gauge. Okay, so again, let me emphasize this point once more and say this once more. Even in magnetostatics, we had used the Coulomb gauge, which is Coulomb gauge condition, which is basically this condition that the divergence of A is equal to 0. But in this, in the case of the dynamical situation where we have, complete electrodynamics, even here it is possible to choose the Coulomb gauge and work in it. It's a very nice gauge to work in. Just that you will find it slightly more convenient, at least for the initial discussion, to work in a slightly different gauge. Okay, which I'll now tell you about what that new gauge condition is. Okay, which makes things slightly more simple in some sense. Okay, at least the initial discussions. So this other thing that, if you remember, that we were in magnetostatics, we had looked at Ampere's law, and then when we recast the Ampere's law in terms of the A, then we said that this Ampere's law particularly simplified if we set the divergence of A equal to 0. So this was exactly of this form, but now we see that here inside this gradient, there is not only the divergence of A, but there is also this term 1 over c squared del phi del t term. Okay, so it is a combination like this. So if I just set divergence A equal to 0, then this equation will remain ugly in some sense. Okay, I mean, this equation, for instance, will keep involving A and phi, and this one also, the divergence of A, this is not going to be 0. So this is going to be 0, and this will be an equation in terms of phi only, okay, because divergence of A is 0. And then perhaps this equation will become simpler, but this equation is not going to become simpler. Okay, so what we can try to do, we can try to select a different gauge condition which sets this combination to 0. Okay, we can say declare that to be our gauge condition. Okay, and that is also a very popular gauge choice or gauge condition choice, and this is called the Lorentz gauge. Okay, this is called the Lorentz gauge condition, and basically, so there are two viable gauge choices. One is this Coulomb gauge condition where you set the divergence of A equal to 0, and the other thing is this Lorentz gauge where you set the divergence of A plus 1 over c squared del phi del t, this is equal to 0. And if you choose this Lorentz gauge, then the good thing that happens is this, in this equation for the vector field, this term goes away, okay, immediately, and we are left with an inhomogeneous inhomogeneous wave equation for the components, for the Cartesian components of the vector field. Okay, so this equation is something which is, we have, it's a nice equation at least. Okay, let's see what happens for the scalar field. okay, for the the Gauss law. Okay, okay, but before we do that, here's a very interesting point. The point is that whether or not this Lorentz gauge choice fixes the gauge condition, completely. Does it fix gauge completely, or does it completely get rid of the redundancy of description? And the answer to that question is clearly no, which can be seen in the following way: that if we choose a scalar field chi which solves the wave equation, we know that the homogeneous wave equation has very non-trivial solutions. We've just discussed that. These electromagnetic waves were the ones where there were vectors, but even without that, we have waves. We have wave solutions, non-trivial wave solutions and their superpositions as solutions of this homogeneous wave equation, right? So this has very non-trivial solutions, already we know that. And if we take one such solution, and if we do a gauge transformation with that chi, so we are assuming that this chi, the field that we are doing the gauge transformation with, now solves this particular wave equation. Okay, so we can go ahead and take any favorite solution of the wave equation and do a gauge transformation with respect to that. So if we do a gauge transformation with respect to that, let's see what happens to the Lorentz gauge condition. This is the Lorentz gauge condition that we had, and we would transform it in this way. Okay, so there will be one term coming from here, which will be the Laplacian on chi term, because there's a divergence which will act on this gradient of chi. That will give me the Laplacian of chi. And there will be another term from here where there will be a double time derivative, d square chi dt square, coming from here. And this will be the combination which appears exactly in the wave equation. And therefore this is equal to 0 by choice, because chi, we initially assumed that it solves this wave equation. So this is equal to 0. And therefore this Lorentz condition remains invariant even if we gauge transform with solutions of the wave equation. So this is clearly not fixing the redundancy completely. Okay, firstly, if we do a transformation like this is a redundancy of description. Now if we do a transformation like this with a chi which solves the wave equation, then the Lorentz condition remains invariant. So this is like, this is the set of functions that the Lorentz condition is not able to fix. So obviously the Lorentz condition is not able to gauge fix completely, but still it is it's a very nice gauge to work in many situations. Okay, and it makes certain things very manifest, particularly relativistic covariance manifest. That is the point why one chooses the Lorentz gauge condition. Okay, but we'll see the advantage of this slightly later. But as far as the present situation is concerned, if we choose the Lorentz gauge, we see that this divergence of a term in the equation following from Gauss law. So just to remind you, this equation followed from Gauss law and this equation followed from Ampere's law. And in this equation that follows from Gauss law, there was a divergence of a term. And by the Lorentz gauge condition, this should be replaced by 1 over c square minus 1 over c square del phi del t. If we do that, then this equation for the phi also gets converted into a wave equation for phi with some source. Whereas, the choice of gauge has been made such that this term goes to 0. So this also remains as 3 components of the gauge field in Cartesian coordinates. They are also satisfying some kind of a wave equation with some inhomogeneous source term. Okay, so basically we have 4. We have reduced, in the Lorentz gauge. In the Lorentz gauge, by a suitable gauge choice, in the Lorentz gauge, our equations for the scalar and vector potentials reduce to, this set of 4 inhomogeneous wave equations. So if we know how to solve the inhomogeneous wave equation, then we would have solved this problem of electrodynamics completely. So now we have to learn how to solve this inhomogeneous wave equation. Of course, if you were working in a different gauge, you will not get this inhomogeneous wave equation. But then, if you solve those equations, then it will be equivalent to the solutions that you are writing down in this gauge. Okay, but you have to be a little careful about the fact that this gauge condition is not fixing gauge completely, and you may need to impose more conditions to fix gauge completely. Okay, that you should keep in mind. Okay, very good. So basically we have to next go ahead and learn how to solve the inhomogeneous equation. Again, that I will do in the next video. So at this point, I have introduced the scalar and vector potential in electrodynamics, and I have shown you that these scalar and vector potentials with the Lorentz gauge choice, where we get rid of at least partially we get rid of the redundancy of description by putting in a condition on the phi and A, these potentials, and that is the Lorentz gauge choice. With that Lorentz gauge choice, both the equation for phi and A, this Gauss law and the Ampere's law, they reduce to certain inhomogeneous wave equation for the phi and A, and these are we have to now learn how to solve the inhomogeneous wave equation. So let me stop this video